Welcome back to our series on data structures and algorithm. Today we are tackling a concept that many find intimidating but is actually quite beautiful: recursion. We are building on our knowledge of basic arrays and logic to understand how functions can solve massive problem by simply talking to themselves. By definition, recursion is a method that calls itself to solve a smaller instance of the same problem. Think of it as a strategy. You take a big overwhelming problem and break it down into smaller sub problems until they are easy to solve. Imagine you are looking for a ring inside a series of nested boxes. You open the big box, find a medium box, open that, and find the ring. You are performing the same operation, that is opening a box, on a different input, that is a smaller box, until you hit the base case, that is finding the ring, which allows you to stop and discard the empty boxes. To write a recursive function correctly, it must have three properties. First one is the same operation, that is the logic remains identical at every step. Second one, different input, the problem must get smaller with every call. Third one, base condition, a mandatory stop criteria that tells the system when to quit. What happens if you forget the base case? The program enters an infinite loop, consumes all your memory, and eventually crashes with a stack overflow error. The system needs that stop signal to survive. Recursion is managed by the computer's stack memory, which follows the LIFO principle, that is last in first out. When a function calls itself, it is pushed onto the top of the stack. The function below it paused and must wait until the function above it returns a value and is popped off. Let's see recursion in a real data structure. If we want to find the value 4 in this tree, compare 4 to 8. Since 4 is less than 8, we go left. Now compare 4 to 5. Since 4 is less than 5, we go left again. Now we found out the logic is repeated on each smaller subtree until the goal is met. Look at the structure. We always start with the base case to check if the root is null or if we found our value. Only then do we move to the recursive case where the function calls itself for the left or right branch. Factorials are a classic use case. To find 5 factorial, the function factorial 5 waits for 5 multiplied by factorial 4 and so on until it hits the base case. If n equal to 0, then it returns 1. Now see the second example, the Fibonacci series, which uses the formula Fibonacci of n equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. While elegant, notice the hidden cost. Look at how Fibonacci of 2 is calculated multiple times. This redundancy leads to exponential time complexity or massive computational waste. Recursion is not always better than a loop. While loops are often faster and use less memory, recursion offers high readability and cleaner logic for complex problems. Recursion is the engine behind advanced algorithms like merge sort, quick sort, and graph depth first search. It is the priority when readability and working with complex structures like trees are the goal. To wrap up, remember that the base case is mandatory to avoid stack overflow. Recursion is about the trade off between clean code and memory uses. Always make sure your problem size is reducing with every call. Now you know how to write recursive logic. Next, we need to measure how fast it is. Join me in the next video for big O notation.